Hello community! Today we're going to talk about link prediction for graph machine learning, and I would like to show you the idea of link prediction implemented in Pytorch geometric and deep graph library. So here we go. Link prediction using graph neural networks. Now, in many industrial applications such as social recommendation, item recommender, knowledge graph completion, something can be formulated as a link prediction, and what it does, it predicts whether an edge exists between two different nodes in your graph. So let's have a look at this. There are two publications you have to know. The first is Link Prediction based on Graph Neural Networks from 2018, and the other one is Modeling Relational Data with Graph Convolutional Networks from October 2017. What they tell you is there is a scheme, maybe you will find it sometimes, it's called SEAL. SEAL stands for Learning from Subgraphs, Embeddings, Attributes for Link Prediction. SEAL. Now you know what SEAL means. The idea is rather simple. You know this idea. Suppose we're given a network graph, a graph with a set of vertices and a set of edges and a set of sampled positive training links, P, and a set of sampled negative training links, E, N. N for negative, P for positive. Now, the trick is simply to temporarily add some negative links, some negative edges into the set of all the other edges. So we increase suddenly the set of our edges in the graph, including some negative training links that do not exist. But remember, when we did some Word2Vec, we had the negative sampling, and more or less we do exactly what we do in natural language processing, we do now here for graph neural networks. And we generate some new node embeddings for the graph G prime, and we have here the set of vertices, but now we have the set of edges combined with the set of edges negative training links. So this is all there is to know about SEAL. Now the implementation is important because you're not going to believe it. We are talking about graph autoencoder. And in the publication I just showed you, there is an encoder architecture and a decoder architecture for link prediction, for the particular task of link prediction. So we know this. We have seen variational autoencoder all over the place. I have a lot of videos about this. But what are they doing here, particularly in graph machine learning? Now, easy. The encoder maps each entity of our vertices to a real valued vector. You know this. This is our node embedding, our feature tensor creation. This is what we do if we learn a GNN. The decoder, on the other side, reconstructs now the edges of a graph, relying only on the vertex representation on the node embedding representation. Remember, GraphML is representational learning. We have a graph structure and we have to find a representation. We have to learn a new representation of the node and of the edges so we can apply our algorithms for graph machine learning. So what it does, it takes a triple of subject, relation, and object, and it applies a function. So we end up with a single value for each edge on, is there a link or is there not a link? This can be something like an activation function, but let's have a look at the theory. What is going on here? Here on the left side we have our encoder, and on the right side we have our decoder. It is not so complicated. Remember, I told you in my last video when we were talking about graph sage, the theory behind graph sage and how we construct graph neural network layers, that we had here the process of message passing. Now, of course, if you have an encoder and you stack GNN layers, your specific GNN layers can be either a graph convolutional layer or a graph sage or a GAT, whatever you prefer. Now here, I would like to show you two versions, a GCN in the Pytorch geometric version and graph sage. We will show you the code. We do the example in in the deep graph learning implementation. So we have here one layer, we have two layers. You remember we are 2 hops then away from our neighborhood. And what we end up with, as I showed you in my last video, we end up with an improved node representation that takes into account the 1 hop neighborhood, the environmental representation, the information that is stored in the nodes, and the message passing that's going on from one node to the other nodes, the message generation, the message aggregation. I showed you 3 different topics in my last video, how you can do this. But here it's important what we get out of the encoder is an improved node representation, taking into consideration the structural information of the graph and of course the information stored in the feature tensors of each node, or even if you have an edge feature tensor, the information of the edge feature tensor. Beautiful. So for each node we have an improved node representation by our GNN layers applied. This is our encoder side. Now, for the decoder, you remember, our input is, of course, the improved node representation of all nodes of the graph. And what we have to do now is to find out if between the nodes there are edges or not. So how we do this? Now, you know this is a matrix, this is a tensor, this is a vector. So what we do always, if we go with graph machine learning, we do a tensor dot over a matrix multiplication. And you will not believe it, we do a dot products of the node representations. So this means here of our vector, of our matrix, of our tensor, the dot product of node representation for each edge. So we have a start node, we have an end node, and those 2 nodes are connected by 1 edge. So our final classifier applies the dot product between the source node embedding and the destination node embedding to derive an edge level prediction. And we do this for one node, for one edge, and for all the different edges. This is the task of our decoder. And then we say, beautiful, this is our auto encoder, decoder structure, and then we have to train it. So let's have a look at this. We are talking about coding. So I showed you here the example of Pytorch geometric. How we do this. Now, easily. If we do it now in a graph convolutional network, you know that it's easy. This is the classical form how we construct the GNN. We have a convolutional layer 1. You see here in the declaration, this is the graph convolutional layer already provided by PyG for us. Then we have a ReLU and activation function. And then we have the second graph convolution layer, version 2 here. And this more or less constitutes our GNN model. Beautiful. Now for this was the encoder. Now for the decoder, I told you we have a matrix multiplication, a vector multiplication, tensor multiplication, and this is exactly what is going on here. And then you do it for all the different edges, and you have defined here a class called net or network, whatever you like. So, and what you do? Well, you have simply a model that you have to train on. So we say our model now is our net with a specific data set with specific dimensions. Yes, we can do this, of course, on a GPU or maybe even on a TPU. We have our classical Adam optimizer, and we go with a specific loss function, and our loss function is here, BC with logit slots. Beautiful. So you know this is the classical way to implement it. And you say, hey, great, so now I have it in Pytorch geometric and also in DGL. Yes, the complete code for link prediction. Here on the left side, you have the PyG implementation, and on the right side, you have the DGL implementation. The difference is here on the left side, we use a graph convolutional network for our GNN layers. And here on the right side, we will use the graph Sage, the improved mechanism over GCN. And I will show you this now in detail, because what we are interested in, I do have a specific video explaining graph Sage in detail in the mathematical content. And now, building up on the last video, we will use now we will code now, but now in DGL. So you see code, if you read the code here and you read the code here, you will find out you can do it in any language if you want. But we will do it in DGL just to have a little bit of an alteration because all my last 4 or 5 videos were on PyG. So now comes the code. Hello community. So today we're gonna do a code. We're gonna code link prediction with the deep graph library, and our basic language is of course Pytorch. So what we have, I hope I have a GPU up and running, beautiful. And then yes, we just say install, and then we install a deep graph library. So satisfied, we have done it, beautiful. And our topic, as I just showed you, is of course link prediction using graph neural networks. Now you know the theory behind it, so it is easy. We just import NumPy, SciPy, we import Pytorch, and we import our deep graph library. So this is the first that we import. So this is an official notebook from Deep Graph Library. So here you have the theory again. They show you in this tutorial, you treat the edges in the graph as the positive edges. Then we sample a number of non-existing edges. We call them negative example or negative edges or negative graph. So a non-existing edge is of course some node pairs, a start node and an end node with no edge between them. Well, what a surprise. Then we divide the positive examples and the negative examples, and we create a training set and we create a test set, and we evaluate the model with any binary classification metric, and our metric is simply the area under the curve. Now, you know about the seal methodology. We do not apply the original seal methodology with the node embedding where we have assigned specific values. We will do an advanced version. So first, of course, we have to load our data set, our graph. So, and with DGL, it is so easy. We have just dgl.data.chara graph dataset. This G stands for our graph, and we have the features that you are familiar with. We have 2,700 nodes. We have 10,500 edges, like in the last video. The dimensionality of our node feature tensor is 1,433. And the task last time was, with the classification of the node embeddings, assign it to 7 different classes. We will not use our classes now because we are now focusing on some link prediction. So we will focus on the edges. And here we start, and this is the very first topic. We have to prepare our data sets. And given that we have a huge data set, we have now to split in a training data set, in a test data set, and sometimes you also want to do some evaluation. So here we go. In this tutorial, they pick up 10% of the edges from the positive examples and from the edges that really exist in the test data set, and leave the rest also for the training data set. Beautiful. So we have 10% in our specific test data set, and 90% goes to the training data set. Great. Now, you know this, how you split up this. We have a lot of videos already on this channel about DGL. Let's just do this. What you end up with is then with DGL remove edges works by creating a subgraph, resulting in a copy. Could be slow for computing large graphs. You can improve the pre-processing, but we just do it with the classical command. And we are here with our GNN model. And as I told you, with DGL, we want to apply the graph sage model. I have in one of my last video a detailed description of the graph sage idea, the mathematical implementation and the coding. I leave you the link here in the description. So we have DGL, we import the sage layer, beautiful, and we create our model with 2 layers, 2 GNN layers, and those layers are specific graph sage layers. So beautiful. We say here convolution 1 is sage 1, and convolution 2 is sage 2. We have in Sage our beautiful message passing algorithm that is beyond the typical graph convolutional layer. And we define very simply the feed forward. We have layer 1, We have then the activation function, the non-linear activation function with the learning happening, with a simple ReLU functionality, and then we have our second stage layer. Beautiful. Yes, you know, the mathematical formula. So now notation. Yeah, as I told you, they call this here the positive graph, where all the edges that are really there exist, and the negative graph, where we just add some non-existent edges. Remember, word to vec, we also had this negative sampling. Now we construct some negative edges in our graph, and we train our model on this. We know it. This is a representational autoencoder that we're going to build. So let's do this. DGL recommends that you treat the pair of nodes as another graph, since you can describe a pair of nodes with an edge. Yes, you can describe a pair of nodes with an edge. Yes, okay. You have the positive graph consisting of all the positive example as edges. So these are the real world edges. And the negative graph consisting of all the negative examples that do not exist in reality, but we use here only for computational purposes. Yes, yes, yes. You know how to do this. Let's just execute the code. And then, as I showed you now in the decoder, we have to take the dot product. The dot product is simply a matrix multiplication. And in DGL, we have this beautiful command I showed you already in one of my last video on DGL coding, that you have here simply the dot product of two. We have a source node feature and a destination node feature. And this is simply done with this beautiful and short command. Then you get a vector, so you need to squeeze it a little bit. Yes. So just execute. Don't forget to execute it. Yes, absolutely. Yeah. If you want another decoder structure, you don't have to go with a simple dot product. You can build something yourself, whatever you like. There is an example that I give to you. You can build another decoder, but we stay with the classical way. We have a dot product. You're familiar with dot products. Let's not make it complicated, more complicated than it is. So the training loop. Yes, beautiful. We are in graph machine learning, and now we come to the ML part. So our model. Our model is, as we defined, our graph sage model with two graph sage GNN layers. So, and then we say we go with the decoder with our dot product, dot predictor. Beautiful. And then what we have to do, we have to compute, of course, the loss function. And you know that we go here with a binary cross entropy loss function with logits. This is defined within DGL, so we just use this. And if you want to do the validation, so as I showed you, we compute for the validation here, the area under the curve, area under the curve. And this is done in the way that you are familiar with. Beautiful. And now we set up the loss and the optimizer. And since we're doing now machine learning on graphs, you're not going to believe it. Our optimizer here also is an Adam optimizer. Please fill in your learning rate or other hyperparameters that you like, the warm-up period or whatever. This is your classical Adam optimizer. And here we go for the training. So what we have? We have our model. Beautiful. We have the positive score and the negative, more or less non-existing core. And we have our loss function. Beautiful. And then we go with our optimizer. We go with our loss. So, and we're gonna print out for each epoch, yes, the loss, beautiful. And then we can check the results. We do here not the classical evaluation, but as I showed you, we go here with the area under the curve for our indication of the evaluation accuracy. And let's just do this. How many steps do we have? Oh yeah, reach, yeah, let's say 200. 200 epochs should be fine. We have a GPU. Oh yeah, that's fast. That's great. So you see, our loss goes down, goes down, goes down. 0.00, beautiful. And our accuracy is at 84%. Now, for such a simple model, you can, of course, improve it and you can add a lot of tuning to these functionalities. But 84% in this very simple model is really okay. So, and this is it. I showed you how to do link prediction. You have to be careful when you do the splitting for the training data set, the test data set, and for the evaluation. But this is a topic I will show you in my next video, as already indicated. But before we switch to the code, let me tell you, my next video, I will tell you something critical. And this critical is about splitting your graph data for your training. Just a hint, there is some problem if you cut graphs in a not optimal way. And it's not depending if you go with DGL or if you go with PyG. Yes, and you have with PyG, of course, GraphGym. This is something very special developed by University of Stanford. But this is just the outlook for the next video that I show you. There is some very specific way how to split out your graph data set for your training data set, for your evaluation data set, and for your test data set. But this is just the teaser for next time. Now we go on and now we train our code. And just to remember, these are our two publications that I showed you. Have a look at the original publication. This is always the best source of information.